In this video, we're going to look at this example that is about two sample hypothesis tests. This one says a bridge construction firm purchases a certain type of shear pin from an outside supplier. Currently, the firm purchases their pins from supplier A. Recently, a sales representative from supplier B visited the firm. Supplier B claimed that their mean tensile strength is larger. As a result of this visit, the construction firm has asked to test this claim using 23 of each supplier's pins and level of significance of 0.05. When a sample was taken, the results were here. Okay, so basically this is a very common application of two-sample test when you're comparing in this case, two suppliers, two populations, quote unquote. And we want to see if the mean tensile strength of supplier B is larger than A. So what we do is we take samples of each one and we do the test. And something that is very important here is that the test sample sizes are less than 30, right? And also, the standard deviation of populations are not given. These are sample standard deviations. So the population and standard deviation are not known. And also the sample sizes are less than 30. So we have to do the t-test or two-sample t-test. Fortunately, we got the results from both samples. We don't need to do the calculations ourselves on the sample data. The average of sample A, average of sample B, and standard deviation of those two samples. Alpha is given, that is 5%. So part A, state the null and alternative hypotheses. So because we're testing whether supplier B is greater than supplier A, right? So to test this claim, and this claim is supplier B claimed that their mean tensile strength is larger. So we want to test whether supplier B is larger than supplier A. The null hypothesis is always mu A minus mu B equals to 0. For the most part, normally this value is 0. Because we're looking at whether there's any difference between A and B. And the alternative hypothesis, because we're checking whether B is greater than A, that means this needs to be negative, which is the same as saying mu A is less than mu B. But we would have to write it down in this form to be basically correct and know that what type of tests are we doing here. It's a one-sided test of type less than. So now we want to identify the test-to-stat and critical region and use the data that are given here to make the conclusion in part C and find the p-value. So let's go ahead and do that. So for part B, what we're doing is, first of all, is an unpaired data. This supplier B and supplier A are two different populations. The subjects that we are collecting data from are not the same subjects, so it's unpaired data. So unpaired data. Standard deviations are unknown. And n is less than 30. So given all of these, what we do is use a two-sample t-test. And this is based on, if I go a few slides back, this is based on the conditions that we have here. The standard deviations are unknown, sample size is less than 30, and we're doing the t-test here. So we have to calculate the t-score. Now this is the formula for t-score, and we have the x-bars, averages for supplier A and B, as well as the standard deviations. We need to replace them with the values that are given here to us. and we know the sample size is 23. So when we replace the numbers here in the t-score formula, we get and we do the math, we get negative 18.43. Now the next step is to compare this test stat with the critical region. So critical region, we reject the null hypothesis if t-score, which we just calculated, is less than negative t of alpha and nu is the degrees of freedom. Well, in this case, this critical value is negative t of 0.05, and, well, we don't know the nu now. That's the degree of freedom. What we need to do is we need to calculate degrees of freedom. And if you remember, this is how you calculate degree of freedom. These are the standard deviations, these are the sample sizes, and this function. So what I'm going to do is I'm going to replace all these parameters with the numbers for this problem and calculate the degrees of freedom. So when we replace the parameters with the numbers, we get to 39.6, and this is a round down operator here, so we have to round this down to 39. So degree of freedom is 39, and therefore we need to find this critical value, negative t of 0.05 and 39. And this value should be read from the t-table. So I'm going to go to the t-table, see what this value is. So here we are at the t-table, and we're looking for t of 0.05 and 39. And keep this in mind. This is the value that we read, and then negative of that is the R critical value. So that means the alpha is 0.05, and that is here. So we're looking at this column, and we need to look at the 39th row. So we need to go down in this column and find 39. So if I go down here at the very end, I'm trying to show this to you, that 39 does not existed, but 40 is there. And when you look at the difference between those values in between 30 and 40, you see it's 1.69 and 1.68. So it's very close to each other. 39 is probably very close to 40. So what I'm going to do is I'm just gonna go pick 40 here, because 39 and 40 are virtually the same. Is 1.684. So here this value is negative 1.684. So now we need to compare or test the stat with this critical value, and obviously we can see that is way less than the critical value. So we will reject the null hypothesis. So we say, since t-score of negative 18.43 is less than negative 1.684, reject the null hypothesis. And by rejecting the null hypothesis, what we're doing is we're saying that, hey, these are not the same, right? These are not the same, and supplier B apparently is giving high tensile strength products, rejecting the null hypothesis. So what we want to do is, this was conducting this test using the critical region. We found this t-score, and we compared it with the critical value. We made a decision. We want to do this using the p-value as well. So if you remember here, this is the type of hypothesis test that we have, and here's how you calculate the p-value. P-value is equal to probability of t of, in this case, 39 less than t-score. So we're going to do that here for part C. p-value is equal to probability of t of nu less than t score, which means probability of t39 less than negative 18.43. Well, let's draw that on the graph. So we know that t distribution is symmetrical just like normal. It just has a more variation. And we're looking for probability of t39 less than negative 18.43. This is 0. Negative 18.43 is very much to the left of the graph. Let's say it's here. And we're looking for this area. It's going to be a very small area, which is the same as probability of t39 more than 18.43, more than positive 18.43, that area. These two areas are the same. And you can see it from the table is virtually equal to 0. If we go back to, I'm going to go back to the t-table and show this to you. So when you look at the t-table here, you see that you got to go to the 39th row and look at the numbers there. And the numbers that you're looking at on the 39th row are the numbers on the graph here, essentially, to the right of the graph. And then the probabilities on the first row, as we discussed earlier, is the probability to the right of these numbers. So if you go to the 39th row, and there is no 39, you can take a look at 40 here. You don't actually see 18.43. The highest number that exists there is 3.55 at the last column. So, and for 3.55, the probability, if you go to the top, the probability is 0.0005. So for 18.43 is probably much smaller. We can safely say that probability of t39 greater than 18.43 is virtually equal to 0. So we can say that that is equal to probability of t39 greater than 18.43, and that is equal to 0. Well, p-value of 0, you make a decision based on p-value by comparing it with alpha. Alpha of the test is 0.05, and when your p-value is less than that, you reject the null hypothesis, which is the same decision we came to using the critical region here. Part D of this problem says construct a confidence interval that is relevant to this problem and use it to verify the conclusion identified in part C. So the appropriate confidence interval here is a one-sided confidence interval because our test is one-sided. And if I go back here, we should find the upper confidence interval, and that is for when mu1 minus mu2 is less than 0. So this is the upper confidence limit that we need to find, and the lower limit is just negative infinity. So I'm going to calculate this upper confidence limit for our problem. We have all the information. We have this t value. It's t of 0.05 and 39, and we have the sample standard deviation. We just need to do the math for this upper confidence limit. And when we do the math here for the upper confidence limit, I just replaced all the parameters with the numbers that we were given. We will see that the difference between mu A and mu B is less than negative 225.7. So the confidence interval is totally on the negative side. You can see that here. It's from negative infinity to negative 225. That means with an alpha of the test is 0.05. That means this is a 95% confidence limit. This is a 95% confidence limit. And what we can say is that with 95% confidence, average of mean tensile strengths of supplier B is greater than average mean tensile strengths of supplier A by at least 225.7. That's what we can say here. The difference is on the negative side, implying that supplier B is larger. How do we make a decision here? Well, you look at your confidence interval and see if delta naught is in there. Delta naught in this case, for all tests, is 0. In most cases is 0. Is not in the confidence interval. So what we can say is, since delta naught of 0 is not within the confidence interval, we reject the null hypothesis. And that means supplier B has greater tensile strength. By at least 225 with 95% confidence. This is the message that you get from your confidence interval.